This is the Math 2260 Chapter 8 review for fall of 2017. And we're going to cover 5 sections in Chapter 8. We're going to look at integration by parts, trigonometric integrals, trigonometric substitution, partial fractions, and improper integrals. So let's get started with integration by parts. So integration by parts essentially undoes the product rule for derivatives. The integral will contain two functions of either x or y. They won't be combined, but there'll be two functions of x or two functions of y that must be separated. And integration by parts does not evaluate the integral. This is a very important thing. It does not actually integrate for you. What it does is it creates a new expression with a new integral that hopefully we can integrate directly. If we can't integrate the new integral directly, then we may have to do integration by parts multiple times. So here's the theorem, right? We have two expressions. One will be a function that we will differentiate. Another will be a function that we will integrate. And when we break it up into pieces, it produces this new expression. So you see we get a term of two things combined, right, minus the new integral. And this is the integral right here that we hope we can integrate directly. And if we can't, we may have to do this multiple times. So make sure you're very, very careful with this negative sign, especially if you're doing repeated integration by parts, because you want to make sure that you are distributing it properly. So there's sort of some guidelines that'll help you when you're looking at these integrals, trying to decide what decisions to make, right? Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Then u will be the remaining factors. So the trick here is, though, dv is going to have to be integrated. So you need to make sure if it's complicated, is it something complicated that you actually know the antiderivative of? If it's something you can't anti-differentiate, then try option 2. Let u be the portion of the integrand whose derivative is simpler than u. So we can pretty much take the derivative of just about anything we want, but it's a lot harder to anti-differentiate some of these functions. So always note that dv will include dx of the original integrand. So let's look at an example here. And so what we have is x times e to the x. So we can't integrate this directly, so we need to split these things up. Well, x is actually easy to take the derivative of, and as a matter of fact, it's going to turn into a constant. E to the x could really go either way, right? Its derivative is e to the x, its antiderivative is e to the x. So guideline 2 says, try letting u be the portion whose derivative is simpler than u. So if we let u equal x, right, then dv is everything else that's in our integral. And I personally like to stack them like this because I want to be able to see my original integral, and then I want to have my new integral stacked over here. So we need to take the derivative of u, which is just going to be dx, and then we need to anti-differentiate v, which is going to just give us e to the x. So using the theorem, it says that our original integral, and so we can see this here, there's the components of the original integral, equals u times v minus our new integral, and these are the components of the new integral. Now our new integral, I can actually anti-differentiate that directly, right? It's going to just be e to the x. So the final answer here is just x e to the x minus e to the x plus c. So make sure you don't forget your constant of integration. If we had bounds, well then this final step would have been when we deal with the bounds. So remember, we may have had to do this more than once, but you'll always have to produce a new integral and then hope that we can anti-differentiate that directly. Right? Let's look at another example. So this is x squared, right, ln of x. Well, we could definitely take the derivative of this, but that would mean that this would become our dv, and I don't know the antiderivative of ln of x, right? So this kind of leads us back to guideline 1. Well, let's take the derivative of this and let's anti-differentiate this. So we're going to let u be the natural log of x. So then dv is x squared dx. the derivative of u is 1 over x dx, and the antiderivative of x squared is x cubed over 3. So applying our theorem, our original integral will equal u times v minus our new integral. Now when I multiply these two together, this x in the denominator is going to cancel one of these x's, so I'm just going to get x squared over 3 dx. This is something I can integrate directly, so I can go straight to the next step. And I'll get x cubed over 3 times ln of x minus x cubed over 9 plus c. So let's look at an example of where we have to do repeated integration by parts. So notice here that one of our terms is x to the n, right? It's actually more specifically x squared. So I know that in two derivatives that turns into a constant. Sine, however, if I anti-differentiate it, right, I'll get negative cosine. But if I take the derivative, I'll get cosine. And sine and cosine will just keep going in a loop, right, back and forth. Sine will become some version of cosine and then sine again and vice versa. So if you integrate x squared, when you take the antiderivative, you're going to keep increasing the power of x, right? So you could just continue in this cycle forever if you pick the wrong u and dv here. So what we want to do is we want to make this our u because we know it disappears after 2 iterations. Furthermore, if one of your components in your integral is x to the n, well, that power of n is actually telling you how many times you might have to do integration by parts in order to solve the problem, especially if it's paired with like sine of x, cosine of x, or e to the x, which are functions that their derivatives and their antiderivatives just kind of loop back upon themselves. So let's let u be x squared. So du, right, is 2x dx. That means dv is sine of x dx, and so v is negative cosine x. So when I apply my theorem, u times v is going to be negative x squared cosine x. And when I subtract my integral, notice it's going to have 2x times negative cosine x. So I'm subtracting a negative, so that becomes a positive. 2x cosine x dx. Well, this is an integral that I cannot integrate directly, right? I still have a 2x times a cosine x, so I actually have to do integration by parts again. But since I've already decided that my x to the n term is going to be u, I have to keep going with that. If you try to switch up your u and dv, you'll actually end up undoing the previous integral and you'll end up right back where you started. So that means u has to be 2x. So then du is just 2 dx. Our dv is cosine x dx, which means v is just sine x. So now, when we apply integration by parts again, I still have my negative x squared cosine x, but where this integral is, right, I'm going to apply my theorem again. So it's u times v minus my new integral, which is right here, 2 sine x dx. So this is an integral that I can integrate directly. And the antiderivative of negative sign is positive cosine. So you can see here that the cosines and sines, right, alternated back and forth as we kept going. And if we had had like maybe x cubed up here, we would have had to do integration by parts 3 times. You would have seen by the sines and cosines would have kept flipping back and forth, because that's why that happens. So we have to make sure that, right, when we're in this situation, we want to always make this our u, so that way we can actually eventually run out of derivatives to take and we can finish the problem. All right, so let's look at one that's a little bit trickier. All right, so this it doesn't look like an integration by parts problem, but it actually is if we rewrite the original integral. So if I write this as secant x times secant squared x, well, now this is the derivative of tangent, and this is something I can take the derivative of. So I'm going to let my u be secant x. That means du is secant x tangent x dx. My dv is secant squared x dx. So v is tangent x. So now when I apply my theorem, we'll get u times v, which is secant x tangent x, minus the integral of secant tangent times tangent, so that becomes secant x tangent squared x dx. So this would require another integration by parts, right? But you got to be careful, because if you try to separate this into tangent times secant tangent, you're going to end up undoing the thing we just did, and you'll just end up back with secant cubed. So what we can do here is we can use one of our Pythagorean identities, which says that tangent squared x equals secant squared x minus 1. So by replacing the tangent squared with this substitution, we can rewrite this integral, and hopefully it turns into something we can integrate directly. So what we have here is secant times secant squared minus 1. So I'm going to distribute the secant x. And I'm going to get the integral of secant cubed x dx. So see, this minus sign made this negative secant cubed. But when I distribute the secant x, I'm going to get a negative secant x times the negative 1. So this becomes plus the integral of secant x dx. So notice here that we got a secant cubed again, right? And this is why I keep writing this line here, because sometimes this will happen when you have trig integrals. So because this is a minus secant cubed, I can actually add this over to the other side, and now I'll have 2 of these. So this becomes 2 times the integral of secant cubed x dx equals secant x tan x, right? So this guy was moved, and this has a known antiderivative. So the way I remember this is, well, secant is 1 over cosine, and right, the antiderivative of 1 over u is natural log, right? But the derivative of secant is secant x tangent x. So what this actually ends up becoming is the natural log of secant x plus tan x. And you do need those absolute value bars, because you can't have anything, you can only have positive values inside natural logs, right? Plus c. So it looks like we're done, but we're actually not, because the original question asked, well, what was the integral of secant cubed? This is the expression for 2 times secant cubed. So all you have to do at the end of the problem is divide everything by your constant. So the integral of secant cubed x dx is 1/2 times secant x tangent x plus the natural log of secant x plus tangent x plus c. So these are some really common integrals that you can see using integration by parts. So notice here that these all have an x to the n component, right? And they're paired with functions that I said where the derivatives will kind of loop back around. So, right, so e to the x will always remain some form of e to the x. Sine and cosine will keep swapping places. So what you want to do in these cases is you want to differentiate the x to the n term, and you want to integrate this term if it shows up, right? So this will allow you to reduce this eventually down to 0, and then we can bring this back. And usually what will happen in these is if you make this u to the n, you'll eventually reduce this down, and you can see we actually did this for our x squared sine of x that we got a little bit earlier. If you have integrals of the form x to the n, right, all these have an x to the n, but you're looking at ln of x, arc sine, or arctan, well, you can't anti-differentiate these expressions. So these have to become the thing you differentiate, and then you'll anti-differentiate x to the n. But if you know what the derivatives of these guys look like, they are powers of x. So we actually did an example of this where we had x squared times ln of x, and we saw that what the derivative being 1 over x actually ended up reducing that down, and we were able to just use a power rule to finish the integral. The third type, though, however, is a little bit dicier, right? So notice these are combinations of two different things that keep cycling back around. So usually what's going to happen here is kind of like what happened on that last example we just did, where you'll actually see the original integral reappear, and then you can add it back over to the other side, and that will allow you to stop, because these guys will just keep looping kind of in an endless loop, and you may have to do repeated integration by parts on these two problems. All right, so there's one more method we can use to do integration by parts, but it only works when you have an x to the n term paired with a function that's derivative kind of repeats and cycles back on itself, right? And this is called the tabular method. So we already established that if we were going to solve this integral by hand, right, I can tell that I'm going to have to do integration by parts twice. And we said that we would want our x to the n term, right, to be the thing we take the derivative of, because we can bring it down to 0. And we would want dv to be everything else. So what the tabular method does is it literally lets you set a table. Okay? So the first column of your table is going to be sine, and we actually mean like as in like plus minus, right? The second column is going to be the u's and their derivatives. And the third column is going to be dv and its antiderivatives. So you'll always start with a plus sign, because the theorem always has positive u times v. That's how it always starts off. So I'm going to put x squared, and I'm going to put sine 4x. And you'll know how many rows you need on the table by the u column. You take the derivative of your u term until you get down to 0. So the derivative of this is 2x, then the derivative is 2, and then derivative is 0. So this only works when you have an x to the n term. Then we have to anti-differentiate this all the way down. So the antiderivative of sine is negative cosine, but because of the chain rule here, I'm going to have to divide by a 4. So I'm actually going to have negative 1/4 cosine 4x, and then I'm going to get negative 1/16 sine 4x, and then I'll be back at 1 over 64 cosine 4x. So because of the chain rule, I had to keep dividing by 4. You can always check this column by taking the derivatives all the way back up in reverse order, and everything should work out back up. The signs here alternate. So this is a minus, this is a plus, and this is a minus. And this has to do with the theorem, right? Because you subtract the integral, so then if you do it a second time, you have to make sure that that subtraction sign then gets distributed. So the way that you read the table is the following way. Remember that the first column here is not v. The first column is dv, right? So when we do our first anti-differentiation, that brings us back to v. So here's the way we read this. You go straight across, right? So you have a positive u times v. Then we'll read the next column, and then the next column, and we know we're done. And this is why I had to take this down to 0, was because I had to have this row so that way I could get my last v. So now we'll simply read this across. We'll get a positive x squared times a negative x squared over 4, or negative 1 over 4. So this is going to give us that the integral of x squared sine 4x dx equals negative x squared over 4 cosine 4x, right? Then I go to the next line. I have a negative 2x times a negative 1/16, so the 2 is going to cancel, and I'm going to get positive x over 8 sine 4x. Then the next row says take a positive 2 and multiply it by a positive 1 over 64, so that reduces to 1 over 32 cosine 4x plus c. So I would have gotten the same exact answer if I had done integration by parts by hand 2 times. All right, so the next section talks about, well, we just looked at how do you deal with integration by parts when you have combinations of different types of functions, right? What this section says is, well, what do you do when you have two functions of x being multiplied, but they're both trigonometric functions, right? So there's going to be 2 types that we're going to look at in this section. We're going to look at combinations of sine and cosine, and then we're going to separately look at combinations of secant and tangent. So for sine and cosine, there's actually some guidelines we can use to help make this a little easier for us. So if the power of sine is odd, okay, and positive, then what you want to do is you want to pull one of your sines out to save for your du, and then you want to convert all the remaining sines into cosines using the Pythagorean identity. And what this allows you to do is this allows you to do a u substitution where u is cosine x, right, and du will be negative sine x dx, right? But if the power of cosine is odd, then we pull a cosine factor out and we convert the remaining cosines into sines using the Pythagorean identity. And so the idea here is that u is now going to be sine and du is cosine x dx. So if you have an odd number of them, you pull the thing that's odd out. You just pull out 1 to save for your du, and what you're doing is you're creating a u substitution situation, and those are kind of pretty easy integrals to deal with. However, if neither one of the sine and cosines are raised to an odd power, then what we can do is we can use this identity, and we may have to use these more than once, to turn the squared terms into just a single power of cosine, and that's something we can integrate directly. And we may have to do this more than one time. All right, so let's look at an example of putting these guys in practice. All right, so the first thing you want to do is you want to scan, and if either of these are odd. Now remember, if they're both odd, then rule 1 or 2 kicks in. It doesn't really matter. You just pull one of the, you just pick which one you want to pull out, and then you convert over to the remaining one like so. All right, but in this case, only sine is odd, so that means I need to pull one of these sines out and save it for my du. So that leaves me with sine squared x cosine to the 4th x times sine x dx. So this right here, sine x dx, is going to become my du, so I need to turn the remaining sines into cosines. So I'll do that by using the Pythagorean identity that sine squared is 1 minus cosine squared x. And I can simply say, okay, let's let u be cosine x dx. Then that means du is negative sine x dx. And since I don't have a negative sine x dx, I only have a sine x dx, I can take this one step further and say, well, I'm just going to replace sine x dx with negative du. So then what I'll do is I'll say, well, this gives me a negative, that's going to be my negative du, I'm just pulling the negative 1 out front, 1 minus u squared times u to the 4th times du. So then I'll distribute my u to the 4th. And I'm going to go ahead and put my negative sign back in here before I anti-differentiate. So this just reverses the order of subtraction. And now when I anti-differentiate, I'm going to get u to the 7 over 7 minus u to the 5th over 5 plus c. And then I'll put back in what u was. U was cosine x. And there we go. All right, so what we have here is a situation where cosine is raised to an odd power, and even though sine is in the denominator, it's still just raised to the 1/2 power because that's all the square root is. So I can rewrite this integral as cosine squared x over the square root of sine x, right? And I want to pull one of those cosine x's out to the side, and so this is going to become my du. So that means I need to turn the remaining cosines into sines. And once again, I do that using the Pythagorean identity. So that means cosine x, right, is 1 minus sine squared x. And I'm going to rewrite this denominator as sine to the 1/2 x. And we still have our cosine x dx right here. So now I can say, well, let's let u be the sine of x. And that means du is cosine x dx. And so our integral is now 1 minus u squared over u to the 1/2 du. Since there's only a single term in the denominator here, I can split these up. And I can say, well, 1 over u to the 1/2 is just u to the negative 1/2. U squared divided by u to the 1/2 is u to the 3/2. And so now I can just anti-differentiate using the power rule. So this becomes u to the positive 1/2. When you divide by 1/2, right, we flip the fraction. And then I'll have u to the 5/2 divided by 5/2, which means it's really multiplied by 2/5 plus c. And when I replace u, which is sine of x, I get 2 sine to the 1/2 x minus 2/5 sine to the 5/2 x plus c. So we looked at what to do when sine or cosine is odd, but what do we do when it's even? So we said, well, we're going to have to make a substitution. And the first thing I want to do is I want to write this in powers of cosine squared, because my substitution says that cosine squared of x is 1 plus cosine 2x, right, all over 2. So I need to rewrite this in terms of cosine squared. So this integral can be rewritten as cosine squared x quantity squared dx. So I want to make this substitution in right here. So we'll say that's the integral of 1 plus cosine 2x, right, all over 2 quantity squared dx. And just to make this, I have to expand this out, and just to make the math a little easier, I'm actually going to pull the 1/2 out front, but keep in mind this 1/2 is squared, so I actually have to factor out a 1/4. So now I'll FOIL this guy out. All right, and so I'm almost ready to integrate, but notice when I expanded out, I ended up with another cosine squared term, and this is why we said you may have to do this more than once. As a matter of fact, the power right here is telling you how many times you're going to have to end up making that substitution. So if I plug it in again, one thing to keep in mind, it's doubling the angle. So this is cosine squared of 2x. So when I plug this in again, it's going to double it. It's going to become 1 plus cosine of 4x over 2. So let's make this substitution. So I still have my 1/4. I'll have 1 plus cosine, 1 plus 2, excuse me, cosine 2x plus 1 plus cosine of 4x all over 2 dx. So before I integrate, I want to clean this up just a little bit. So I'm going to leave my 1/4 out front. And this 1 is really plus a 1/2 because each of these are over 2. So 1 plus 1/2 is 3/2 plus 2 cosine 2x plus cosine 4x over 2 dx. So now I'm actually ready to integrate this. So the 1/4 stays out front. We'll have 3/2 x. Remember, the antiderivative of cosine is sine. So I'll get 2 sine 2x, but then I have to divide by 2 because of the chain rule. Then I'll get plus cosine of 4x, right? It's over 2, but I have to divide by that 4, so this ends up being over 8. And then I'm just going to multiply my 1/4 back in just to clean this up. So my final answer is 3/8 x plus sine of 2x over 4 plus 1 over 32. Oops, sorry, this should have been a sine. I think I said it but didn't write it. And there's our final answer.